Okay, so continuing on with our chain rule lesson, we need to realize that it's very, very possible to have a function of three variables, like we see here. W might be a function of x, y, and z. However, x, y, and z might be functions dependent on r and s. And that really does complicate matters considerably. Whereas in the past problems, we would have all of our variables x, y, and z dependent on perhaps just one variable, maybe just t. We're seeing that this can definitely complicate matters. We can have many variables as independent variables. You can see r and s are independent variables, x, y, and z are intermediate variables. This little chart here, w or u as I wrote for this last problem, is a function of x, y, and z, but x is a function of r and s, y is r and s, and z is a function of r and s as well. If I'd like to take a derivative of w now, of course ultimately the two independent variables are r and s, so we could either take the partial derivative of w with respect to r, or we could take it with s. In this preliminary, in this first rule of taking a chain rule, we can see that we might choose to take a derivative with respect to r. I've highlighted the tree to help guide us through that. W, I crossed it out, but imagine it's still up there. W can be linked to r through x, through y, or through z. And this tree actually does prove helpful. So I could take a partial derivative of w with respect to x, but then multiply by the partial derivative of x to r. So this is our little chain rule here. Then we could take our partial derivative of w with respect to y, multiply that by the derivative of y with respect to r. Finally, add to that the derivative of w with respect to z, multiply by the partial derivative of z to r. We could do the same thing with respect to s. Real quickly, let's look at a last problem. I hope this will explain what we just were talking about. So we have a function u, and I'm going to write u up here. It looks like u is a function, if you just look at this preliminary equation, it's a function of x, y, and z. X, y, and z, though, are going to be our intermediate variables, because x, y, and z are all functions of r, s, and t. So this really does complicate things quite a bit. And we can see that if I am asked to find the derivative of u with respect to s, the big question is, how can u be linked to s? You can see right here on this first pathway through x, of course. We can also go through y. Finally, we can go to z just as well. So that's really where we're going to be taking our derivative with respect to s. Of course, we could have taken partial derivatives with respect to r or t as well. Now, before we move on much further, I do want to say that not only are we taking a derivative, but we're given initial conditions. We're given that r is equal to 2, s is equal to 1, and t is equal to 0. Keeping that in mind, realize that the intermediate values for x, y, and z can be found by plugging 2, 1, and 0 in for r, s, and t. So looking above, x is r times s times e to the t. That would be 2 times 1 times e to the 0. Well, e to the 0 is 1, so we would get x is equal to 2. Similarly, we could say y, of course, would be r, which is 2, times s squared, which is 1 squared, and then e to the negative 0. Well, e to a 0 power is 1. 1 squared is 1. Once again, we'd get y is equal to 2. Finally, with z, we would have r squared, which is 2 squared, times a 1, But the sine of t, sine of 0, thankfully sine of 0 is 0. And 0 times all of those other values will arrive at z equals 0. So look, we not only have initial values for r, s, and t, we also have values for x, y, and z. You can do this every time, even before you were to take a derivative, if you're dealing with initial values. But let's go back to our little tree diagram. I'm going to take a partial derivative of u with respect to s. Now, how do we arrive at that? Well, you can see by our tree we could have partial derivative of u with respect to x. Here's that first path that we can have. But then, using our chain rule, we'll say the derivative of x with respect to s. Then I will add to that this little second pathway. We can have our partial derivative of u with respect to y. And in this middle branch coming down, we'll have the partial derivative of y with respect to s. Finishing this up, we'll take the partial derivative of u with respect to z, and then multiply by the partial derivative of z with respect to s. Right now, we just have to work this all out. Go back to the original equation and take the derivative of u, which is up here. Whoops, let me erase that. I wanted to have it highlighted. Take the derivative of u with respect to x. Well, treating x as the only variable, we would get 4 x to the third y. The second part of this equation just collapses out. There are no x's in it. Let's take the derivative of x with respect to s. Well, x is r s e to the t. The derivative of s is just a 1. Treating these others as constants, we'd have r times e to the t. Let's move on and go back to our original equation, taking the derivative of u with respect to y. Well, my first term, the derivative of y is a 1. X to the fourth we treat as a constant. For our second term, derivative of y squared is 2y. Could we move z to the third out in front? Certainly we may. But now let's take a derivative of y with respect to s. We'll bring down the 2 and write 2rs e to the negative t. All these other parts of the problem are really just constants. And then we'll go back to our original u, take our derivative with respect to z. The first components completely disappear. The derivative of z to the third is 3z squared, so I'll have 3y squared z to the second. And then dz ds, looking over here, well, there's only one s right here in the middle. The derivative of s is 1. We're left with r squared sine of t. Now, if this was all we were asked to do, we'd be done. We could say very nicely, hey, we found our derivative. However, we're going to plug in r equals 2, s equals 1, t equals 0, x equals 2, y equals 2, and z equals 0. As we do that, let's realize with x is 2, this is 4 times 2 to the third. Our y is also a 2. Our r is a 2, but we'll have e to the 0. And of course, e to the 0 is just going to become a 1. We'll have x, which is a 2, 2 to the fourth, plus 2 times 2, and then very nicely 0 cubed. Well, 0 is going to wipe all this out. But then we're going to multiply to 2 times r, 2 times 2, times a 1, times e to the negative 0. Finally, for our very last term, if we're really on our toes, we're going to be very happy to see z squared, because z squared is 0 squared. What we know at this point is that 0 is going to wipe out this last grouping altogether. By the way, sine of t, sine of 0 would do that as well. So this very last term is a 0. It's going to be gone. Let's see, 2 to the third is 8. 8 times 4 is 32. 32 times 2 is 64. 64 times 2 is 128. And of course, e to the 0 is 1. 2 to the 4th is 16. This all wipes out. 2 times 2 is 4. 4 times 1 is 4. And here's another one. So 16 times 4 is 64. And as we add all this up, I believe you would get 192. What this is really saying, and I want us to get more and more used to seeing what this partial derivative of u is with respect to s. What this is really saying in this regard is, with this initial condition, when r is 2, s is 1, t is 0, and your x, y, and z values are corresponding as well, what you're saying is u is changing at a rate with respect to s of 192. That means, think of it as 192 over 1. For every increase of 1 unit of s, u would increase by 192. So that's just putting some things into perspective. Well, hope this goes well. Best of luck to you.